Hello, this is a quick video on how you can decode CAN messages with a spreadsheet and an oscilloscope. First you get the CAN high and the CAN low signals hooked into your oscilloscope. In the yellow I have channel 1, which is my CAN high, and in the pink is CAN low. And you can see the CAN frames are separated. And what I'm going to do is I'm going to use the oscilloscope to begin decoding this. So I'm going to go in and push the decode button on my scope. It's still not decoding any messages. You can see there's no data here and there's no CAN frames being shown. And so I can go in and adjust the signal threshold voltage. And I want the threshold voltage to be just below the noise line on the top of the CAN high there. And now you can see my CAN high is being decoded. I can also decode CAN low, and it should have the exact same values, but I also still need to adjust the threshold voltage there so it's also just below its high value. And so now I'm decoding both my CAN high and my CAN low signals. And what I can do is I can hit the run stop button. Now that I have all these frames, I can see several frames on one screen. I'm going to zoom in because I want to investigate what a single CAN frame looks like and why do they have these numbers. Why is it decoded to what it has been decoded to? And so I slide the time scale over here, and now this is one CAN frame. And you can see it begins with CAN high going high for a while, then it dips down, goes back high. And CAN low is always doing the opposite. When CAN high is high, the CAN low is low. And so this prevents, I guess, errors from happening because they should always be returning the same message. And so what I do is just copy and paste the picture of the signal into Excel. And then I just divided the columns up to be the same width of the signals here. And so I type in 0 where CAN low is low, 1 where CAN low is high. And I did that through the entire CAN frame. And then there's a thing called bit stuffing in CAN. Every 5th bit has to be flipped if it's the same value. So the message begins with 5 zeros, so there has to be a stuffed 1 here. And everywhere where there's 5, I guess in this case it's 5 zeros, then it has to flip with a stuffed bit. And what that means for us is those do not count. They're not part of the data. So we start with our start of frame bit, and then we're followed by 11 arbitration bits. So there's 1, 2, 3, 4. This one doesn't count because it's a stuffed bit. 5, 6, 7, 8, 9, 10, 11. There's our arbitration area. And what this area tells us is the CAN ID. We go back to our scope and we see the ID is 0x, which means hexadecimal, and the hexadecimal number 7, which is the same as a decimal 7. And we go up to here. Oh, this is still our stuffed bit. Don't want to confuse that with any of that. We have all the zeros in our arbitration followed by 111, which is the decimal number 7. So the 111 here becomes a 7. And after this we have our remote transmission request bit. And then we have 6 bits that are going to be our control frame. And that tells us, well, let's count them out here rather than do it this way. 1, 2, 3, 4, 5, 6. And the control frame will tell us how long each of the data frames are going to be. And 1, 0, 0, 0, 0, that is 8. So we have 8-bit data frames. And so now we can begin decoding our message. And so since each data frame is 8 bits, here's our first, second bit, This is not counting because that's a flipped stuffed bit. Third, fourth, fifth, sixth, seventh. There's another stuffed bit, and 8. And so our number is 0, 0, 0, 0, 0, 1. And binary 1 is the same as decimal 1. So there's our first frame. And then we can go and count frame 2. We have our first bit, second bit, third, fourth, fifth. This doesn't count again because it's a stuffed bit. 6, 7, and 8. And now our number is 1, 0. When in binary, that is, or 1, 0 binary is a 2 decimal. And then we go up to our third data frame. 1, 2, 3, 4. We don't count the stuff bit. 5, 6, 7, 8. 1, 1 in binary is 3 in decimal. So we've decoded our first 3 data frames already. And then we go into our fourth. 1, 2, 3, 4, 5. Don't count the stuffed bit. 6, 7, 8. 1, 0, 0. That is a 4. And then we'll go into our fifth. 1, 2, 3. Don't count the stuffed bit. 4, 5, 6, 7, 8. 1, 0, 1 in binary is 2, 4, 5 in decimal. Then we go to our next data frame. 1, 2, 3, 4, 5. Stuffed bit 6, 7, 8. 1, 1, 0 is a 6 in decimal. 1, 2, 3, 4. We do not count the stuffed bit. 5, 6, 7, 8. 1, 1, 1 is in binary is 7 in decimal. Then we go to our 8th and final data frame. 1, 2, 3, 4, 5, 6, 7, and 8. And what is it? We have 1, 0, 0, 0, 1, 2, 4, 8. That's 8 in decimal. And then this goes into our CRC, which is called your cyclic redundancy check. And this is just to make sure all of there were no errors in the transmission. And this number here in 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, that means 45B in hexadecimal. So the binary is up here in the gray, and the hexadecimal is 45 Bravo. And we can go into the scope and make sure our CRC is indeed 45 Bravo. And that is how you decode a CAN signal using an oscilloscope and a spreadsheet. Hope it helped you out.